Cool. What is an electron configuration? What is it? Coipus. Yeah, it's an address. There's 4 parts. What are the 4 parts for the electron address?
Energy levels. Sublevel.
Orbital and spin. Cool. So just like your address has 4 parts, right? The state, the city, the street, and the house number. So too do our electron addresses. If you have all 4 parts of this, then you have only one electron you could be talking about. How did we identify our energy levels? What did we use to show the energy level? N equals, who said it? Whole numbers, yeah. N equals 1, N equals 2, et cetera, which is a big whole number for our energy levels. Cool. Sublevels, get the letters. What were the 4 letters? S, P, D, and F. We're just taking the energy levels and we're splitting them into smaller groupings or subsets. And then within each of these sublevels, they actually tell you the shape that the orbitals take, how many go in each orbital. How many per orbital? Remember? It was the pairs of electrons, right? 2 electrons in each of those orbitals. S was for sphere, P for peanut, P-E-A, nut, sorry. D for double peanut, and F for flower. The flowers are kind of funky. I had no real good way of showing these on the video, right? But how many would fit in there? An orbital is how many? A pair. So it's weird to think about. So when we say the orbital shape, we're saying, okay, we think about an atom. Where are the protons and neutrons? In the nucleus, right? You want me to turn that off? Is that distracting? Just a weird inception piece. Cool. So our protons or neutrons here in the center. And then our electrons are floating around the outside, right? We're trying to figure out where are those electrons most likely going to be. And so it is kind of funny. It's kind of weird to think about. We say, if this is our nucleus, let me center it a little better. If this is our nucleus, our electrons are negative. What's the charge on our nucleus? Positive. There's protons and neutrons in there, but protons are positive. The electrons are held in place by the nucleus. So we always start with our first energy level closest to the nucleus, because it's the positive nucleus pulling those electrons towards the center. Here's energy level 1. This would be N equals 2. If I had another one around here, it'd be N equals 3. So we just divide them into energy levels. Sublevels are within each energy levels. We identify them with letters. We just kind of are being more specific. We can have an S in the first one. In the second, we can have an S and a P. In the third, we can have an S, a P, and a D, because as we get further out, we get a little bit bigger, S, P, D, and F, and then the same all the way up. And so you'll notice as they get further out, they get larger. But when we're talking about our orbitals, we're saying, where are we going to find them? What shape of a field will we locate those electrons in? So is it in a spherical shape? Then in our peanut shapes? Is it in our double peanut shapes? This is just talking about the actual physical location. And the spin, how do we show the spin? Spin, spin, spin. Coming out of the notes, I think. With the arrows. Yeah. This would be a clockwise arrow, counterclockwise arrow, right? Clockwise spin or counterclockwise. To be fair, at the individual level, we don't know which is which. We just assume one is positive or clockwise, the other is counterclockwise. Usually we assume it to be clockwise, but you could argue for either. We just know they have to be different, because otherwise they can't fit in the same place. So I think that's a recap of the notes. How we doing? Now the question is, what the heck do we do with that, right? If you would grab 4.5 for me real quick. 4.5 should look like 4.5 should look like this. Should look like this. And so we'll start on the front side. If it's the side that has hydrogen at the beginning. Oh, hydrogen's a good one. So if we want to know, sorry. And show me. This is a good musical. If we want to know where the electrons are located, first thing we need to know is how many electrons are in there, right? How do you find the number of protons? Let's start there. By the atomic number, yeah. So we look on the periodic table, find hydrogen. We'll do hydrogen first. You find hydrogen. What is the atomic number for hydrogen? 1. If it's, there's nothing written here on the hydrogen, that means the charge is 0. So if we have 1 proton, we would have to have 1 electron. For all these, you can assume them to be neutral, and the protons will equal the number of electrons. How are we doing? Clear as mud. So far, so good? Number of electrons, I think this is throwback to last week, right? For pen numbers. Cool, now we want to know where that electron is. Well, what's the first energy level? Energy level 1. We're going to start by filling. You're going to like this. There's going to be a pattern here. We always start by filling in the closest energy level to the nucleus. So we would start with energy level 1. So the big number here represents the energy level. What's the first sub-level we can split it into? I think there's only 1 in the first energy level. It is the S. And now, how many electrons could we put in here? How many electrons total can you put in an S? You guys remember from the video? It's pretty little. Not 1, but 2. There's a maximum of 2 electrons you could put in here, but we only have 1. So we'd say, boop, there's 1 in there. So if we're thinking about our parts, let me change colors here real quick. Fancy, I know, right? If you think about our parts, the first number here is the energy level, so E level. The S, or the letter, is the sub-level. And then the exponent represents the actual physical electrons. S's can only hold 2, P's can hold 6, D's can hold 10, and S can hold 14, max. Oh, look, hey, we're done. We're done with our first electron configuration. That's not so bad. Ooh, as I erase it. Oh, there's got to be a faster way to do that. Cool, but we could be a little more specific, right? Because what shape is that S orbital going to take? S is for what? Sphere. So we can actually think about in 3-dimensional space where this electron is going to be found. It's going to be found in an S orbital, which is just a pair. And we sometimes, for simplicity's sake, we just drew the lines here over on the orbital notation. But technically, this would represent a sphere, right? Ooh, where would the 2s be? The only thing that's different is the number. Where's 2 going to be? Closer or further from the nucleus? Further. So technically, this second 2s is a sphere a bit bigger, right? Further out from the center. P represents peanut, so there's an up and down peanut, side to side peanut, and front to back peanut, right? Ooh, what would a 3s look like? Yeah, it'd be a sphere, but bigger, right? You can see why we don't show the shapes every time, right? Because it gets real messy real quick. So oftentimes, instead of drawing all the shapes, we just put these lines. The lines represent the shapes. Here's where we find a pair of electrons. And so for our hydrogen, we only have 1. We know it's in the first energy level, in the S sublevel. In this sphere, I'm going to do a half arrow. You'll see here why in just a second. I'm going to do just 1 arrow in that first 1s orbital because I only have 1 electron. How are we doing? Arrows. And if you're sitting there going, I don't have any idea what's going on, don't worry. We're going to do some more examples. Again, we're just giving the most probable location. Let's jump down to sodium real quick. Sorry. Sodium. How many protons for sodium? Wait, how many did you say it and I missed it? Did you say it and I missed it? Oh, I think it's far left. Sodium. 11. If it's got 11 protons and it's neutral, it's got 11 electrons. Ba-doop. All right, we want to know where these 11 electrons are at. Well, where would the first 2 go? in the first energy level. Yeah, in our 1s, we could put 2 in there. Okay, cool. But now the first energy level is full, right? So now I gotta go to the second energy level. We can have a 2s and a 2p. How many can we put in s's? 2. How many can I put in my p's? 6. This is a pro tip from having done this about as long as you've been alive. I like to clump them in groups of 10 because it makes the math easier for me. I know I need 11 electrons total. I just used 10. Ooh, but my second energy level is full. I filled up all my S's and P's in the second energy level. Where do I go now? The third energy level. We'd fill the S first, and you could put how many in there?
2.
You could fit 2, but we only have 1 left, right? So it would be just a 1 there. Here's your electron configuration for sodium. 1s2, 2s2, 2p6, 3s1. Yay! Here's where we find all of its electrons. Whoa. Hey guys, this is heady stuff. Like, this is weird. Technically, if you want to go home and sound really fancy, be like, we did quantum physics today in chemistry. Because this is all based on quantum probability. So if you're sitting here going, we're going to be okay. Cool, now we got to show the actual orbitals, because if you look at, for example, that 2p, if I said, okay, that 1 electron was in a 2p sublevel, could you tell me which one I was talking about? It's still 1 of 6, right? So that's why we actually have the orbital notation. We can actually be more specific. And first thing I would do is actually fill in my arrows. So we've got, let me make sure I'm on the right line here. We've got 2 in the 1s, 2 in the 2s. We've got all 6 in my p's, and 1 in the 3s. I'm just doing half arrows because it's easier to draw them. Hope that's okay. We doing? Clear as mud. So now, here we go. So if I said, oh, nope, that's not gonna work. Grab my highlighter. If I said, no, that's not gonna work either. Okay, I'll just change colors. So now if I said you have a down arrow, right? Counterclockwise spinning electron. So this electron here, right? In the second p nut, in the p sublevel, in the second energy level. Now I've got all 4 parts. There's only 1 electron I could be talking about. And it's that one pointing down in the middle of the p orbital. Whole goal is to get it so that we're describing the probable location of just 1 electron. How are we doing? Questions? There's only 7 of us. You got questions? We can get them answered. All right. Real quick, let's hop over to 4.4 for just a second, because I think we need to look at a weird thing going on there. So let me close. So if you drop over to 4.4, 4.4 actually shows, I think, 4.4 actually shows all of the notes you took from the video, right? Down here in the bottom right. I think that's an overview of all of the notes. Hang in there, guys. You're doing great. Want to draw your attention to the stuff on the left. Now that we got all the parts and we've seen some examples, I wanted to take you through. There's technically 3 rules. We got 3 rules. There's all the rules. There are 3 rules that we got to abide by when we're looking at electron configurations. And the first is off-bow. The off-bow principle. Off-bow is, it's kind of fun to say off-bow. There's a lot of vowels in there. Off-bow. Off-bow is German for to build up. So it is the building up principle. You're going to love off-bow because he or they say the off-bow principle means that there's a pattern. All we got to do is get the pattern. And then once we run out of electrons, we stop and we're done. Off-bow principle, building from lowest energy to highest energy. Hund says that electrons are greedy. It's kind of like the kids on the bus, right? First kid gets on the bus, where do they sit? First back seat, right? Back left, sure. Second kid gets on the bus, where do they sit? Back right. Next kid gets on the bus, where they sit? Upper row, but back left, back. So as kids get on the bus, we each get a seat, and then what happens? Next kid gets on the bus. Every kid's got a seat, and another kid gets on. What do you got to do? You got to buddy up, right? The same is true for our electrons. Our electrons are going to fill each orbital. If it's all the same energy, they're going to fill one at a time until they have to pair up. Anybody notice when I did the arrows, I did up, 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 and then down, down, down for the peanuts? Everybody catch it? We'll see an example here in just a second. Turns out they want to spread out. They want to be by themselves as we're thinking about our three-dimensional space. Cool. Pauli exclusion principle just means you can't have the same address. Can't have the same energy level, same sublevel, orbital, and spin. Something has to be different. Otherwise, your IRS tax return will go to the wrong house. That'd be bad, right? Can't have two people with the same address. It's gotta have different addresses. Something has to be different on that address. How are we doing? I feel like I'm hitting this fast, but nobody's asking any questions. Is it because I'm recording where we don't want to ask questions because we're recording? Okay. We're just not sure what questions to ask. Okay. Cool. If you would take a piece of paper or your notebook, something, and start at the bottom. Start at the bottom of the screen. Start at the bottom of the screen. We're going to fill up some electrons. So we're thinking about off-bow. Off-bow says we go from lowest to highest. So if we start at the bottom and start working our way up, what do we fill first? What do we hit first? The first energy level, the S. We can put how many electrons in there? 2. 1 up, 1 down. Cool. What do we hit next? 2s. We can put 2 electrons in there. What do we hit next? 2p. Here's Hund's rule, right? We're going off bow, bottom up. Hund's rule says all these seats are the same amount of energy. I'm going to fill 1 in each first. Each kid gets their own seat on the bus. And then we go back and we buddy them up. Then we go back and buddy up. What do we hit next? 3s. We can put 2 in there. What do we hit after that? 3p, up, up, up. I just do ups by convention. We don't actually know which way they're going, but we usually do one and then the other. Then what do we hit? What do we hit next?
3.
What do we hit next?
3.
What do we hit next? It couldn't be that simple, could it? Let me ask you a question. Would you rather, right? I feel like this is a fun game, right? Would you rather make one sphere bit bigger or make 5 double peanuts bit smaller? One bigger thing, right? And so we actually see it's kind of a zippering effect. We actually fill the 4s, the s fills, then we go back to all the double peanuts, fill them in, and then we go back to that 4p and fill those in. If I had more room and I could get another screen on here, you actually then hit 5s. You hit 5s and then you go back to 4d. There's kind of, it's like a zipper. They fit together almost like a zipper in terms of how their energies work. But that's the biggest kind of delineation or kind of break in off-bows rule. We always do the S of the next level before the D's. Should we look at an example of one of these? So back to 4-5 again. You guys are being good sports as I make my video here. Boop, boop. So let's look at, I don't know, calcium. Calcium's a good one. Let's look at calcium real quick. We're going to do a configuration, an address. We first need to know how many electrons. How many electrons for calcium? Huh? 20 for calcium. Cool. If it's 20 protons, we can assume it to be neutral. We got 20 electrons. I like it. So we got 20 electrons. Oh, I got to click on the pen first. Nope, not background. There we go. 20 electrons. Oh, I should do that in black. Sorry. Cool. Where do we start? 1s. How many can we put in there? 2. What's after 1s? 2s. We can put 2. And then what? 2p. We can put 6. We're up to 10 electrons. We have filled the first and second energy level, so we got to go 3s. We can put 2 in there. After 3s, we got 3p, you can put 6 in there. Before 3d comes 4s. You can put 2 in there. We got another 10 here. 10 and 10 is 20. I think we're done. Cool. Now we just got to do all of our arrows, right? It's going to feel a little funny here, isn't it? I'm off a row. So we got our 2 in the 1s, our 2s, our 2p. Ooh, I need to zoom in. Our 3s. Says we fill one at a time. And we're actually going to skip the 3D all the way over to our 4s. How we done? Orbitals, electron configurations. Oh, we only got one thing left. What is it? What's left? Last column. What's last column? Lewis structures. Oh, cool. Should layer in quick. To be fair, normally we would cut it here and we'd have you practice a bunch of these, but I want to get you that last column so you can be practicing that. Do your bio teachers proud? Have you heard of the thing called valence electrons? Valence electrons? What are valence electrons? So it's Christmas time, right? Middle of winter, and your heat goes up. What do you do? Huh? Your heat went out, right? Middle of winter, heat. You're gonna call somebody, right? Then what? It's getting cold.
Blankets.
Put on blankets, plural. Okay, cool. Still cold.
Heater.
Well, power's out.
Fire.
Yeah, so you make a fire in the fireplace. So you sit next to the fire, you got your 3 blankets on, sure, why not? You got 3 blankets on, fire, and then all of a sudden the fire does that thing. It always does it, right? It goes, right? Pops, and that ember spits out and gets on your blanket. You're like, ah! Right? You put it out real quick. Which blanket gets ruined? The top or outermost, right? When we start looking at our electron configurations, there are special electrons. We call those our valence electrons. They're the ones in the outermost shell. They're the ones that are going to react with other things. They're going to be super important for us when we start to look at our compounds and our chemical reactions. We call those our valence electrons. Those are the outermost electrons. Outermost electrons. And we use our Lewis structures to show how many valence electrons we got. So our Lewis structures just show us the valence electrons. We're going to show them with dots. We're going to show them with dots. And so we would look at our outermost energy level. Look at our outermost energy level. X here is just the element symbol. And then we're going to fill in some dots. And remember, our electrons like to spread out. So we do 1 on each side, and then we buddy them up if we have to. 8 is the maximum number of valence electrons you can have. And if you don't believe me, you'll find out. 8 is the maximum number of valence electrons we can have. So let me give you an example of this, because I know I'm kind of flying here. Don't worry, we're going to get lots of practice. Just trying to maximize our time, guys. So if we look at our calcium here, go back to our calcium here. On our calcium, what's our highest big numbered energy level? 4. In the entire 4th energy level, how many electrons were there? 2. So for our Lewis structure, we want to show those 2 electrons. We put our element symbol in the middle. In this case, it was calcium. We had 2 valence electrons. We're going to put 2 dots. 1, 2. You just put 2 dots. Can we look at a funny one? Let's, this will be good practice. Go ahead, write the electron configuration for aluminum real quick. Did you do aluminum for me? It's 13. Oh, spoilers. Element 13. Oh, try 13 for me, please. Okay, that's nice. We're working on that with Hugo. Please and thank you. Manners. Come on. Good for us to practice. Something like this? 3p1? I'll admit, usually I just check the end, because if your end is right, I know you got all of the ones before that. Cool. What is our highest energy level for this one? 3. In the third energy level, how many electrons? 3. So for our symbol, we have aluminum in the center. And then we would do 3 dots. 1, 2, 3. All of the electrons in the outermost center. How are we done? Cool.